Hello everyone, good morning. People are still joining, so we'll start the webinar at 11:05 sharp. I'm repeating, like people are still joining. We will start the webinar at 11:05. People are still joining, like we'll start the session at 11:05 sharp. Yes, so I got the confirmation. So good morning, everyone. My name is Vatan Sharma. I welcome you all on the behalf of MIDAS IT team for the webinar series that is a finite element modeling and analysis of hydropower structure presented by Chetan Agrawal sir. This is the eighth session, this is the eighth session and the last session of this webinar, which is on the nonlinear static stress analysis, crack propagation analysis, and the linear time history results and interpretations. Before going towards the today's content, I would like to request Chetan sir to provide a brief recap of the previous sessions for the audience. I'm making you presenter, sir. So now you are a presenter, sir, and you are not
Can
audible,
you,
sir. Yes,
am
sir.
I audible
Yeah.
now? Yes.
Yes, sir. Yes, sir.
Okay.
Yes.
Okay. Thank you, Vatan, and I welcome you all to this session of the webinar. Uh, well, I'll give you a brief recap uh, of the last session. In the last session, I put the modeled modeled NOF dam block for dynamic analysis. This setup I had created in the previous session, in the fifth session. Okay, in the last sorry, in sixth session. So in the last session, I just put it for the analysis, and then we discussed this code. Okay, so actually. I just wanted to, uh, uh, I mean, tell you one story, what you call earthquake story. I'll try to draft it. Okay. See, for any analysis, say if we have a say static load, okay. See, on the upstream side there is a reservoir here, and there is a static hydrostatic pressure here. You know the Newton's second law, that is F is equal to ma. This body will have some acceleration because of the force. Okay, force is equal to mass into acceleration. Suppose there is some vibration also, some say some machine is moving over it. Okay, so this any part of this dam will also, I mean, vibrate. It will be because of that vibration. Okay, so that will also create some deformation, and if some deformation is there, that means some induced force is there. Okay, so first thing is deformation is because of the static force. Second thing is deformation is because of what, the I mean, for the vibration, okay, surrounding it, which is creating some dynamic vibration is there, which is creating deformation. Okay, and third thing is, suppose in some part of this dam block is having a loose material, say some earth is there. Okay, so because of its lesser elasticity, that part of um, that particular part of that dam will deform more. So this so we have to solve this dam, for that matter any structure, for these three components. First, mass into acceleration. Second, this vibration, and with the vibration, we have to multiply it with the damping constant of any material. That will depend on the damping, that deformation. Okay, damping into velocity of which with which this particle vibrates. Okay, mass into acceleration plus damping into velocity. And third one is the stiffness, modulus of elasticity, stiffness into its deformation. So that will define the total induced force in that particle. So only so we have to solve um, our structure for all the forces for these three parameters only. Okay, so this is what we had studied in the code also. So in the code, first thing is when during in the early 20th century, okay, when we could not simulate the ground motion time history, we could not simulate the shaking of the ground. We have only option to analyze our structures manually. So how to analyze it for the earthquake forces? That was a big challenge. But we were aware of the time periods. Time period means I mean the different material behave in a different manner. Okay, suppose you are sitting in a car and suddenly driver applies the brake. Okay, so your head may shake, but your rest of the body will not shake. Okay, and that your head will have some time for one to and fro motion, and then after some time it your head will then again become still. So that will be the time period of your head. I mean, it will be maximum at the initial initial time, and then it will reduce. So, and maybe if you are say standing in a metro train, okay, and your entire body is shaking, so that time your time period will be different. Okay, so but I mean you have a same material, your body is behaving differently. Okay, suppose you have a tummy tucker, what you call that, that vibrate for reducing your fat, then your stomach will vibrate in a different manner, but material is same. Okay, so for different vibrations you will have different time periods. I mean your frequency of vibration will be different. So similar is with the structure also. So with different uh, shapes, modes of vibrations. Okay, the structure can vibrate in a different manner, in one particular direction, in another direction, in some other direction. It can twist also, whatever. So it will have a different time periods. Okay, so we can plot a curve between time period and the acceleration of that structure based on the damping properties of that. So that curve is called response spectrum curve, as the acceleration response of that structure versus the time. So in the earlier 20th century, people know that this is there, and people have recorded the accelerations of the ground motion also. That also seismologists know. Okay, so we have acceleration due to maximum acceleration of the ground motion, plus we know the behavior of the structure, the time period and vibration of the structure depending on its damping properties, that also. So scientists then, I mean this seismologists and the technocrats, this is set on, I mean in a room, and they decided how to apply this earthquake force, because we can't simulate the ground motion at the time, and at this we can only apply the force. But actually seismic force is not directly applied on the structure. Ground shakes, and based on that shaking, the structure above it shakes. But how to solve it analytically? Then it was decided that whatever the peak ground acceleration is there, of that ground motion, multiply it with the mass of the structure and apply it. Okay, so when that was applied, the structure was becoming quite, I mean, quite heavy, quite big. The sections were coming quite big of any structure, whether it is a building structure or dam structure or anything. So then they decided, let us reduce this acceleration to half. Then they reduce that peak ground acceleration to half, z by 2. Okay, then multiplied it with the response of the structure based on the time period of that. With that coefficient, they multiplied the mass and applied that force, and to get the reactions. Even then, I mean, some structures, those are fine, and I mean, some unimportant structures, it is found that this is again uneconomical. Those structures are not, I mean, of that importance, that their failure is not catastrophic. So maybe we can include one more factor, that is importance factor. So they include one more factor called importance factor to it. So peak ground acceleration divided by 2 into SA, the response of the structure, into importance factor. And then they found, even then the sections are coming out to be quite large. For dam importance factor, they considered 3, because their catastrophic failure will be there. The entire city can wash out because of the failure of the dam. or maybe buildings. It can be fatal also for some people. 1.5 for certain buildings. For one, which is not, I mean, where the loss of life is not there, maybe importance factor of 1. Then even then, the sections were uneconomical. Then they decided, let's see up to what extent structure can not, I mean, totally damaged, not break. It can have some plastic hinges, it can go beyond elastic limits. So that reduction factor they apply to this factor, that is called response reduction factor, and they come out with the seismic coefficient for that, and that force they applied. Again, that force is not applied on the CG. I mean, for see, if ground shakes, the upper part of the body shakes more. That means the force is, the seismic force is not at the CG. So they then came out with another mechanism of varying the force from top to bottom. Okay, from in dam it is 1.5 times of seismic coefficient at the top, and this dam is founded on a sound rock, which I mean vibrates in phase with the sound rock. I mean, the material of rock and the concrete is almost similar. So that alpha h variation, the seismic coefficient variation, is 1.5 at alpha h at the top and 0 at the bottom for dam. For building it is different, because building is a portal frame structure. Okay, so it is different for that. And up to say ground level, the alpha h is considered, and beyond up to 30-meter depth, so the variation is say half of alpha h to half, but whatever it is. And the variation of force is also different in buildings. In other structures it is different. So so that mechanism was I mean postulated, it was developed for applying the seismic load at that time. And then for safety criteria also, how to, what should be the safety criteria for that, they have, so some people sit together and they decided that about 1% of during the earthquake, if say we have applied this, so if say 1% of, so tension will be there, because when the body will vibrate, there definitely some tension will be there. So on the upstream phase, if the tension is, we can restrict to say 1%, I mean, then we can assume that dam is our safe. So they come up with 0.01 times of FCK for earthquake case. And for say, if say uplift is also there, extreme uplift is there, so probably that is a very rare phenomena, they come up with some other number, 0.02 times of FCK. So all these numbers, all these codes, everything, those were formulated for the analytical solution. But now we have this what you call finite element method with us. We can actually simulate the actual geometry of our structure. We can actually simulate the ground with the actual properties, actual geotechnical properties, and we can actually simulate the shaking of the ground. We don't have to apply the force on the structure itself. Let the structure behave as per the shaking of the ground. Okay, so and then those criterias are not applicable here. Those criterias, I mean, the best at the moment we have the criteria mentioned in US Engineering Manual 6051. Those, if we apply those criteria, 0.01 times of FCK or 0.02 times of FCK here, our structure will again become huge. Okay, because now we are analyzing our structure for peak ground acceleration, maximum acceleration of that ground motion. So Rafaels has provided that permissible allowable tensile stress on the upstream face of the dam. Now the, now I think codes needs to be revised for numerical solutions. Those for these finite element time history analysis, those clauses of previous codes are not applicable. So this is what we have studied. Rest you can go through that code. So I think this is it, Vatan, from my side. uh,
Thank you, sir.
you can please proceed. Yeah, you can please proceed with
Yes.
the today's presentation. Yes.
Yes, sir. Thank you, sir. Thank you for the story and telling you how we generate that Z by 2 I by R and SA by G. Thank you, sir.
Yeah.
And now we are moving towards the presentation. Okay, so I'm making a presenter myself. So my screen visible? Yeah. It's now it's, let me check the audience view. Yeah, it's visible. So I'm changing the.
So welcome you all to this session of the webinar. I'll start from where we left in the last session. So in the last session, we had seen in E condition, there are many nodes. There are many time steps where the factor of safeties are less than 1. So you can see here in this curve up to say about 3 seconds, it is okay. But from 3 seconds to 8 seconds, there are more than 50% cycles which are having the factor of safeties less than 1. So there is no such criteria, as I told you in the previous session. And this band, this from 3 second to 8 second band, this is the most critical one, and we are getting the factor of safety is less than 1 in more than 50% of cycles. Okay, so we'll try to reduce this number. Okay, at least say in this, say 60 to 70% in time cycles, we should get more than 1. So and another thing is, I mean, more than this time history, uh, I think this lesser uh, base pressures on the heel side, B, C, and D, B, C, and D. Okay, this is also, I mean, although this is as per the codal provisions, it is okay. In normal operating condition, there shouldn't be any tension here. The resultant should lie within the middle third of the base. So that is there. Okay, I want to increase the base pressures here, B, at least on B, C, and somewhat to D also. If so, say if some differential settlement is there in the uh, in the foundation. Okay, see, if we have some although the if we have some flexibility in the foundation, if we consider some modulus of elasticity, these base pressures will further reduce. Okay, but if some differential settlement is there, then at this particular location particularly, and probably at C location, I mean, there is a possibility that it can be in tension practically. So I want to have at least say about 250 kilonewton per meter square at, or 200, I mean more than 200 kilonewton per meter square pressures at B and C, and in D also at least 50 kPa pressure. Okay, so that I have more confidence on this time block. Okay, so what we'll do, we'll change this upstream slope a bit. Okay, so that we have more uniform base pressures. I mean, better than what we are getting from this slope, and the factor of safety against sliding for time histories also, those also improve. So this is the intention first. Then we will perform uh, the stress analysis. So for putting more weight on the upstream side, what I'll do, I'll change the work plane first. 3 points to this plane. Okay, create one surface to here. Okay, and mesh, I'll remove this interface, I'll create again. Okay, and then I'll merge these nodes, because why I'm doing this exercise, so that my nodes, all these nodes along with the nodes of the rock layer, both these will move certain distance, you will get to know. Okay, so then merge these nodes, merge all these nodes. When we create interface, one additional node is created in between two nodes of these materials. One gap is created, so we have to merge these nodes when we delete the interface, so that these nodes are interconnected. Okay, so merge these nodes with a very small distance, whatever is the default distance, and click OK. So you see here 107 nodes merged. Okay, so now Okay. Anyways, so now for this geometry, move this. I mean, I'll increase this by say 5, 6, 7 meters. Okay, and I'll have a slope here. So translate this 2 points, say by 7 meters. Okay, let's keep it 7 meters. Okay, and firstly put all these meshes off, and then maybe we can rotate it about these 2 points by say 10 degrees or whatever. I mean, we'll start, you can optimize this dam by changing these slopes. Okay, so let's say 10 degrees, need this. Okay, now I can project my nodes to this mesh, project these nodes, unselect the so I just want to project these I mean the face nodes only, not the inner nodes. Okay, so maybe you can unselect these some inner nodes like this. Okay, if some inner nodes are there. Okay, then select this shape. Okay, direction, this direction, and okay. Okay, so with this now you can so this rock layer nodes have also moved. Okay, so and we have all the loads are applied here, and all the loads are fine. I mean, self weight won't, it will take the self weight itself, hydrostatic FRL, two components. Okay, it will automatically change whatever will be the components here. Okay, I mean, so there won't be any change in normal tailwater level. Silt load will automatically change as per this slope. Hydrodynamic pressure will change, seismic inertia will change. Only thing is we have to I mean change these uplift pressures. Okay, so for that again we will repeat the same exercise as we did earlier. So we need only this M20 concrete. Okay, we put off this static loads. I have to change the material properties, and have materials, I have to go 3D edit. Oh sorry, materials instead of property. Change it to 10. Oh sorry, 0. Yeah, what I am doing. Okay, I have to model water. Again, same thing, extrude. This we have done in previous sessions, so you know this. Okay, I'm presuming that you know this, what I'm doing. Okay, then change the work plane. I mean, we are doing this exercise to get the reactions for the uplift pressure, changed uplift pressure. Okay, rest all other loads won't change. Okay, so now then we have to change the constraints also. Let's say water I'll remove. Static analysis constraints I'll put here. I want reactions at the interface. I'll rename to something else, say uplift. This constraint uplift. Okay. Okay. Some other constraints are also selected. Okay. Maybe I can edit this. I don't want the nodes, these nodes. Okay. Okay. Now it is better. Next, I have to change the uplift function. It's also so. Actually, this maximum uplift sometimes in some of the codes and some of the, I mean, clients want that in flood condition we should apply maximum uplift, okay, instead of normal uplift. This ninth, actually it is maximum uplift. Okay, anyways, so otherwise maximum uplift is not required with for in different codes in engineering manual 2200 and in Indian code also only normal uplift needs to be considered in operative and drains in operative and inoperative condition. Okay, anyways, let's change the function now. So I'll be applying only these, I'll be changing these functions only at the moment. So now this x value has changed. Let me check the x value. What is it? Oh, we have changed it 7 meters. I have moved it now. So it is 68.05. Is that? So instead of this 68.05, okay. And this one also add it 68.05. Okay, so this ninth load case I'll correct it. It doesn't look good. It's not normal, it's maximum. Okay, okay, then what? Then I have to create a load case here. Oh, I have to apply this self weight. Where is that normal uplift? Normal uplift drains operative. This force I'll delete. I'll get it from that Excel sheet as we did earlier. Remove this. Okay, and with these two I'll add self weight. Apply and normal uplift drains inoperative. Okay, okay, then on this. Okay, and apply the pressure. Go to static load, uplift pressure at the space, 3D element face, select this face. Okay, normal or whatever. Okay, I'll select here. So this normal uplift drains operative 1. Okay, it is normal uplift drains operative. Apply. Okay, and normal uplift drains inoperative. Okay, same faces I have to select. Okay, and here also normal uplift drains inoperative. Okay, okay, now so with gravity I'm analyzing it. So I have inputted the density of concrete as 0 just to get the reactions here as I did earlier. So uplift, I'll change it. So it's fine. Uplift reaction uplift. Okay, I have defined it. That is fine. Normal operative drains inoperative. Okay, so then solve it. will take some time, 1 or 2 minutes. Okay, just wait for a minute or so. Guess it's performing fine. So let's put off this water. Okay, now I need the reactions. Go to results, extract. I need reactions. Sorry. I need reactions that to in Z direction. For both, I'll consider. Okay, select the nodes. Okay. So again, you may find some internal nodes, but their reactions will be zero. Reactions will only be there at the supported, I mean the nodes with the support. So I'll delete it in Excel wherever the reactions are zero. Okay, and get the tables for TZ. Okay, got this table, copy it, paste it in that Excel sheet for uplift. Okay, then I need these values only. Copy, paste it here, paste special and transpose. Okay, same exercise which I did earlier. I'm repeating that. Okay, data, text to column, space and column. Finish. Let us see, sort out for data sort from column B or C, whatever, smallest to largest, so that I have all the zeros with me. So these nodes have zero values. Okay, next, this is the reaction, upward force, but I mean downward force. So we have to apply it in the upward direction. So multiply these values with the -1. Okay, now go to the main sheet. Okay, just delete these first. Okay, normal uplift. This is fine. Okay, then copy these nodes, copy, paste the nodes here. None 0 0, this will be 0. I just need the Z forces. Okay, so Z will be this one for normal uplift. Paste special values and number format. Okay, and this will be force. Now I have this 7th, I mean load case 7 also. So just copy it, drains inoperative. That also I can keep it here only. Okay, and I'll just copy in, but nodes and these values are same for this. So paste it here. Only the reaction will change. Let's see the reactions. Okay, copy these reactions, copy and paste it here. Oh, paste special. Let's see. It seems to be okay. Save it, close it. Okay, then close this, go to modeling mode, and now import. Static analysis, import. So again, software will take some time. Okay, it has done it. So it will take some time to importing it. It has done it. Let's see. So it has imported it the same way as we did earlier. Okay, so now we have the uplift pressure with us. I don't need gravity and these, I just need forces. Okay, remove it. Okay, next, see this kink. See, there can be some tension at this kink, so we can make it somewhat what you call curved here. So for that, That would be better. I'll change my work plane to this plane first. Okay. 2D lines. Okay. This. Okay. I mean that this will be a curve with say 150, 175 radius. Okay. With say this tangent and this tangent. Okay. So even this small curve will help to reduce the tensile stresses on this face. Okay. Now intersect this with this. Okay. And then delete. Okay. Now we have this. Now I can create a surface here. This one, this one, this one. Okay. Extrude the surface. I mean this exercise I'm doing to get the surface at this, and then I'll project my nodes as I did earlier. Okay. Then extract this surface, curved surface, and now I can delete these. Okay. And now I can project these mesh set. Mm, okay. These nodes to this shape at shortest path. Okay. So it is. So these nodes are moved now. Okay. So actually, see, I mean, you may say that this mesh is not fine. See, you can refine the mesh later on, but for the initial analysis, just to get an idea of the stresses, okay, you can have this sort of bigger elements, okay. And later on also, if you refine the mesh and do it again, I mean, it will take just 1.5 hour to complete this exercise. I mean, modify the geometry and remesh it. Okay. So you will find the stresses are not that apart. Whatever stresses you will find here, so those the similar stresses you will get after you have a refined mesh. Okay. Mm. So we have all the loads with us. Okay. And uh, actually, mm, I have edited this video in and removed that water mesh, only that thing. So other than that, so this mesh is there now. I have to. What I'll do. I'll I mean analyze uh, this case. Okay, for all the load cases. Okay, and no. See, I'll add it. I just need M20 and M25 concrete and boundary set only uplift that boundary set and these. Okay, I'll analyze this and compile all the results. Then I have to I mean these coordinates of these nodes will also change, so I'll compile the node. I mean I'll extract the node coordinates again and then put it in my Excel sheet for the stability check. Okay, and afterwards I'll also change the raft properties, that will also change. Okay, and let's see the stability. So I'll resume the recording after I input all the data. Okay, and check the stability. After getting, see, for stability, I mean, if you go by the code for static stability check, our dam was stable for that. Now the stability will improve with this slope. So we'll see that. Okay, and next we'll start the stress analysis. Firstly, we'll be checking the stresses for load condition B, uh, and because that is a normal operating condition, we have to make our dam safe for that. Okay, then we'll be performing the stress analysis for uh, load condition E, that is normal operation plus earthquake, and then load condition H, that is for MC condition, considering the provisions of engineering manual 6051. For load condition B, I'll be following engineering manual 2200 and IS 6512. I mean, those are almost similar, the criteria for that. Okay, so I'll analyze it separately, and then we will, I'll resume the recording. So I have tabulated the data here and changed the this raft properties also. Okay, so this has increased. I mean, I have stressed this by 7 meters, and this coordinate also I have stressed, but whatever was required, it was required 2.969. I mean, and then tabulated all the coordinates and tabulated all the forces again. Okay, one thing actually I didn't realize earlier. So I had not changed the density of these concrete. Okay, so I mean, I changed the density of concrete again to 25 and this to 24 kilonewton per meter cube. Okay, so and then I analyzed this load case, all load case linear static, and so I tabulated all the results. Let's see what's happening. Let's go to say A, so you can see this has improved. Let's go to B, say, okay. See, now at B and C, I mean, pressures are slightly higher than before. Earlier it was less than 200 at C. Okay, so and it is close to 50, 40.67. Okay, let's keep it. Okay, so this is fine. C is almost similar to D. Okay. So actually well, E condition, the D condition, let's see, earlier it was something about 1.25 factor of safety. So now it has increased to 2.19, and this one still actually, see, in this reach still, I mean, the values are less than one in some of the cases, but these, if you, I mean, okay, let's see it. If you plot how many values are having the factor of safety is 1, you will find within this reach it is about 20-30%, it seems, from this curve. Okay, I mean, just from this curve we can have a look at it. It's so it's fine. I mean, we can consider this. And let's see the summary of the forces. Summary of the forces, still we have negative pressures, but the negative pressures have significantly reduced for E condition, normal operating plus earthquake condition. Okay, and it is 1.2 now. Earlier it was 1.17 something, 1.12 or something like that. Okay, so it has also marginally increased. So I think it should be fine. Actually, for this, for A, B, and C condition, the resultant should lie within the middle third of the footing. That means all pressure should be positive. So that is there. You can have a look at engineering manual 2200. There also it is mentioned. And in unusual, these seismic cases, okay, drains operative condition, it should be within the half of the base. Okay, so that means that if we have, say, 1368 pressure, and the negative pressure is of also same magnitude, then the neutral axis will lie at the center of the footing. Okay, so but then again redistribution will also occur, right? So I mean, so let's be on conservative side. If, say, negative pressure magnitude is half of this, then also we can consider that footing is safe. So in our case 1368, so, and say 1000, so okay, so in our case negative pressures are much lesser now. Okay, so this should be okay as per that criteria. And for extreme conditions, drain inoperative, no, extreme condition is H condition, so in this case G drains inoperative also. Negative pressures are slightly higher, but as compared to, so still it is in the half of the footing. So this dam is stable for dynamic as well as and for static conditions. We have established that. Now we will have the stress analysis. For that, first I'll consider uh, uh, I'll consider load case B first. Let's say load B. I'll be having a non-linear analysis. Okay, we'll check the mm, crack propagation also here. Load, static load I'll mention. Okay, say load case B. I'm not checking for load case A, C, and F. Those are also static condition with range. First, I'm just checking it for load case B. You can, I mean, if you want, you can have it. You can check it. So the load case B normal operating condition is, I think, most prominent. We have to make sure that our dam should be stable, uh, perfectly stable, without an issue in normal operating conditions. So I'll check for load condition B. Okay, I haven't provided the interface. I deleted that, so I'll do that. So again, boundary set 1 I'll consider self weight, silt load, then hydrostatic, this normal tailwater level, normal uplift, range operative, and nothing else. Analysis control. Okay, uh, keep this, keep same as it is. And okay, next thing is, okay, so I have this load case B with me now. Next thing is, so I have to change this properties of concrete also to non-linear. So change this property to discrete cracking, or what you call smeared cracking. Okay, and so these are fine, these parameters. Non-linear parameter we have to define tension. Okay, let's define, say, tension. See, okay, I'll go to some background. See, in code it is mentioned that for B condition there shouldn't be any tension in the concrete on the upstream face. Okay, issue is, see, when these softwares were not there, when we couldn't perform the actual numerical analysis, we have to do it manually. In the, I mean, in codes you will find that at I mean at different levels, the way to find the stresses here. See, we can find the stresses as per, say, FRL, I mean hydrostatic pressure at particular level, but how to take the effect of uplift here? So various code provides that at particular level, uplift can be reduced to half, and then some, I mean, some, what you call, permeability, we can assume of the concrete, we consider it half, and then consider it to 0, something like this. So those were for the manual computation of stresses to take care of this. And then in manual computation, what you will find, the weight will balance all these stresses, and you will get a compression here for load condition B. Okay, considering that uplift, whatever is mentioned in the code at different levels. Okay, so actually those uh, criterias are not applicable for the numerical analysis, for finite element analysis. Here we are actually simulating entire dam, and uplift has been applied at the bottom of the face. If you want to include the permeability of the concrete, so that is very low. I think 10 to the power minus 7 centimeter per second, something like that. So uh, it's so that you can provide here, then perform a nonlinear analysis, then actually actual result you will get, how much uplift you will get at different levels here. Okay, uh, and ultimately you won't, there won't be any change in stresses here. So uplift we had provided here, so, and that will be accounted for. But see, in numerical analysis, these nodes, you may find some tensile stress of the order of, say, 0.003 or 0.001 here. That means that our this dam is stable. That means this is in equilibrium. Concrete has almost negligible tensile stress. It is because we don't get any node upstream of this. That I mean some singularity would be there for these nodes to transfer the forces. Okay, so these nodes may have some tensile stress on the face. Okay, but that you have to see how much tensile stress we have. Okay, see, as I told you in the previous session also, the tensile strength of concrete you can consider as FCK by 40. Say M25 concrete, you can consider about 46.6 MPa for the plain concrete. Okay, without considering any reinforcement. Okay, okay, so for numerical analysis, we can't consider zero tensile strength of concrete. That criteria is applicable for evaluating reinforcement as per the bending theories, limit state method or working stress method. There, that is the assumption there that concrete will not take any tension, entire tension will be taken by the reinforcement. Here we don't have reinforcement. Concrete will have some tensile strength. Okay, so I'll create one function here, and we can have various functions function for this. We can input the stress strain curve also. So I'll consider it brittle. So once the okay, I'll change the unit. Actually, I'm not very good with the units, so let me change the units. Where's that? Cancel it first. Okay, so it's Newton and MPa would be fine. Now I'll define that function. Okay, so it won't take much time, just a minute cracking. Okay, if it is taking time for analysis, I'll resume the tension function. Let's keep tension function brittle. So FCK by 40, say if it is M25, it is about 0.6. I'll consider half of that, 0.3. Okay, let's see 0.3. Okay, uh, okay, so I'll consider 0.3 tension function. This is what I've defined. You can have some compression function, shear function also. You can Google it, or you can find it in various literature what shear function we should provide. You have to define this beta. I mean, in code you will find that it is, I think, 1 or something. You consider that. Okay, so automatically it can take. So let's not define the shear. We are concerned about the tension function of the concrete. Okay, and for M25. Okay, so same. Okay, say I'm 30. Okay, we can reduce it marginally, say 70 only, or we can keep same function also, or if you want. Okay, I'll change this. Okay, tension function 1. Okay, const brittle. It should break at what? Again, centimeter. Okay, I'll change that. Point, say 27, whatever. Okay, so it's centimeter. I'll change the units. I don't know why I do this. It should be Okay, now I'll correct it again. Just no, I can correct these functions from here only. Tension function 1. Okay, I can correct these functions from here. You will find these functions appeared in this function list, so it should be 0.3. Okay, MPa, and it should be whatever we have defined, 0.27. Okay, and what else? Now we can solve it. Other things are fine. Edit. Let's see. Boundary set 1, normal uplift. That's fine. Okay, let's solve this. Let's see the crack propagation also, crack widths also. Okay, so it's a non-linear function. It will take some time. Okay, let us start it first. We may find some error here. Just a minute. Okay, meanwhile we can go through this sheet. This is why it is taking so much of time. I don't know. Anyways, I'll resume my recording after this analysis is finished. Then we'll analyze the stresses for load condition B for nonlinear behavior. Oh, it has started. Okay, it has just started. Okay, so it seems to be fine. There isn't any issue with our model. Okay, no, there isn't any issue. Let's see, run analysis. Uh, okay, anyways, I'll resume my recording after this analysis is completed. So the analysis has been completed. It took about 84 seconds to complete that. So it is more than the normal. I don't know. Maybe some other programs are going on in RAM might be busy of my computer. Anyways, so it has finished now. So I mean, I should have modeled interface element also, but for static, I mean, for load condition B, it doesn't matter. So for I should have actually, so that to see the base pressures also. Okay, we can analyze it again. Anyways, let's see the stresses in concrete. I'll just switch on these M20 and M25. Okay, so let's see first stresses, solid stresses, principal stresses. We can see here auto range Newton per mm square, that is fine. Okay, so you can see this entire upstream phase, it is mostly in compression, this color. Okay, let's see the results also. Okay, there is a slight tension on the this edge, so I can have that interface element with compression only behavior. Okay, then there will be distribution of forces. Anyways, we are let's see the results here only. We are more concerned about stresses. We have established that our dam is stable for static conditions, so it is negative. So there is slight tension 0.0035 in some of the nodes on the upstream phase. That is okay for numerical analysis, no issues with that. Let's okay. So there is considerable tension in this lift valve, so we have to provide, not considerable, actually this is also not very high, so red color you will find here, that two at the edges. Okay, so anyways, we will be providing reinforcement in the lift well walls and stairs, whatever. Okay, and we have to analyze it separately for bending moment and shear forces, these flexural members. Let's see the propagation of cracks. We can see the 3D element crack results. Let's see the status of the cracks. So okay, what we'll do, mm, we'll see. Okay, so let's see in M20 concrete, the crack is there at the bottom, as you have seen that some tension was there. Okay, so it is P. I'll change the display mode. Where is that? No results. Okay, say I'll exclude it. So we have some tension here and some tension in the what you call in the lift well region. Okay, that to some minor tension that is more than 0.3 MPa. So where we definitely have to provide the reinforcement, and these are partially open. Okay, so cracks, these are the cracks, and then we can find out the crack widths also and normal. So you can see here, so the maximum crack width is of the order of 0.029 mm, so it is very less. Okay, so this doesn't matter. Okay, let's see for M25. Firstly, let's see the status of the crack. Let's say, consider this wireframe. So M25, let's exclude. Okay, so here you can see there are prominent cracks here, partially open cracks. So these are all flexural member, bending will be there. So that's why, so cracks will be there. The tension will be more than 0.3 MPa in these cases, and crack width, but crack width is still not significant. It is just 0.07 MPa anyways. So reinforcement has to be provided here. So from the numerical analysis, we can consider that our dam is safe for load case B. Okay, so stresses, everything, those are safe. Okay, uh, change it to shading with wire mesh, and then I can have the entire mesh open. Okay, so let's analyze for time history. So similar analysis can be done for A condition, C condition, and F condition, and check the crack widths. Okay, and see if in future if I record videos for flexural members, say TG foundation, not flexural members, I mean thinner members like TG foundation, or see where the reinforcement is actually required from the stresses. I'll show you the crack width, whatever we evaluate manually, that actually matches with this crack width after putting the reinforcement. We can model the reinforcement here. Okay, and then we can perform nonlinear analysis considering some tensile strength as I have considered 50% of FCK by 40, the same with the same tensile strength, almost same crack width you will find. Okay, so here actually this is a gravity structure, only some tension is there in this wall, otherwise there is no tension at all. So let's perform the uh, time history analysis, ground motion time history analysis, and check the stresses for that. For that, we have to again define this dynamic load case, ground acceleration x. Okay, firstly we'll consider, say, load case E. Okay, dB again minus 0.12, and z direction vertical, dB vertical, that is 0.08, and load case C. Actually, later I realized that earlier I had input this 0.05 instead of 0.08 when I was analyzing for dB. I corrected that, and then tabulated the results accordingly. So the results which I had shown you, this was considering vertical scale factor of 0.08. Okay, so okay, so load case E I have defined. Then I have to define, I mean add the load, the normal operating loads to this load case E. So there is option here for in the dynamic loading case, time varying static load. This is what we have. This is what we have to define here. Self weight without any function with scale factor of 1. Add it. Next, upstream hydrostatic pressure we have to add with this time history, and then normal tailwater also we have to add. Okay, then silt load we have to add. Then see hydrodynamic, I have not modeled water, so hydrodynamic also I have to add. So seismic inertia, it will compute as per the I mean ground motion. So normal uplift range operative I have to add. What else? Next, nothing. Okay, so this is load case E. Okay, so now I have defined this. Again I have to create one analysis case, load E. Okay, so this is time history direct, same thing I have to repeat. Okay, defines time step, say T2, whatever name you want to put it here, 8.01, add. Okay, 8 seconds, fine. Analysis control, we don't have to do anything. I don't want to put this really mass proportional and stiffness proportional for this, so click OK. And this one, OK, boundary set 1, click and load E, and OK. And again I forgot to model the interface element. Go to mesh, interface, plane. Okay, select this mesh set. So it will create two interfaces, one because it is connecting the two materials, one bottom layer and then another the dam. So go to wizard, same thing. Okay, meters, actually again I have to change the units. Meters I'll keep, so otherwise I may do something wrong. Okay, wizard 0.05 whatever. Okay, rigid link, create plane interface. Let's see, it might have created two interfaces, this and this. Okay, so just remove this interface, delete. Okay, so earlier in earlier midas we had to manually merge these nodes. Now once the interface is removed, it automatically merge the nodes. Okay, so this is a good feature in the latest MIDAS. So now it is fine. So load case E I was analyzing. So now interface also. So interface is also considered here. That is fine. Okay, let's solve it. So let's wait for a minute. Once the analysis started, I'll stop this recording and resume after the analysis is completed. So 800 seat has started. Let's see if everything is fine with the analysis. So it's okay. So it seems okay. So it has started the analysis without any error. Okay. So I'll stop the recording now and see time step 1 it has started. Okay, I'll resume my recording after all the 800 step increments are finished, increment 2. So it will take about 15-20 minutes. So I'll resume the recording after I get the results, after the analysis is finished. So it has finished. So now we can check the stresses. Okay, so if you want to see the animation, you can see the animation as we have seen for when we analyze for dB. Okay, so relative deformation is something like this. Anyways, so okay, let's see the animation. Won't take much time. Okay, this instead of this, let's see the stress animation in principal direction. Okay, auto range Newton. Let the unit should be mm. Okay, so this is for one particular time. After this, let's see how the stresses are varying. Firstly, and you can see the tensile stresses of the range of 3.69, and this is a linear analysis. So if it is non-linear, I mean some tension would be there in the base. Okay, let's see the animation first. This rendering, it will take some time for rendering, and then it will start the actual animation. Okay, this is not the actual one. In the initial cycle, the deformation would be almost 0, and then it will start from say about 2 seconds. Okay, so look, it will take some time for rendering, then the actual animation will start. So what we will do, see, this is another sheet for evaluating DCR, demand capacity ratio. Okay, so I'll be using this sheet. So what I'll be doing, I'll compile all the tensile stress in one particular node. Say if say some tensile stresses are induced in on the upstream phases somewhere. Okay, those nodes, and for each time cycle I'll compile that data, and then I'll see only the tensile stresses. Okay, compressive stresses I won't consider. See, compression also, see, for plain cement concrete compression, you can consider about how much by 3, say M25 FCK by 3. So if it is M25 by 3, it is about 8 MPa, 7 MPa, 7 to 8 MPa. Okay, so compression, I don't think there would be any issue. For tension, of course, we have to check the DCR criteria as per USAC Engineering Manual 6051. So for that, I need the all allowable tensile stress. So here, say if it is so outer actually concrete, I'm keeping as 20. This Raphael's formula, as mentioned in USAC Engineering Manual, this is in foot-pound system, that consider foot-pound system 1.7 FCK raised to power 2 by 3. So this is in FPS. 1.7 factor is for FPS system. PSI, pounds per square inch of that concrete 28-day concrete strength. So I'll converted this M20 to PSI. Then as per FCK, this formula 1.7 Raphael's formula I have applied. So this much PSI strength we can consider. Okay, for DB condition, for DCR value of 1, And if I convert this PSI to MPa, so it comes out to be 2.38 MPa. Okay, so for each time, these are the step values, and these are the stresses induced in MPa. Then DCR is computed, induced tensile stress divided by the allowable, and for plotting the curve, this is only the time step. Okay, so for various time step, so in this particular region, so it is exceeding for few cycles, that DCR criteria of 1. So we'll see for our case. So let's see, has it finished? Yeah, it's almost finishing. Let's see the animation first, just 2-3 minutes to just have an idea. Okay, so animation has started from 0 seconds. So slight animation is there. Okay, so this high stress, it is, I mean, somewhere here. Okay, so I mean, this color, it is ranging from zero point 0.8 to this much. Okay, so here we will provide reinforcement. It might be in some what you call some edge node or some deformed, badly shaped element. This much high tensile stress. Otherwise, stresses are less than 1 MPa, zero point 0.6. Okay, it is somewhere, it is exceeding also in some cases. We'll see that. Okay, so this is how it is vibrating. Okay, let's stop it. We are more interested in the stresses. Okay, in concrete. So this is a conservative design. I have considered massless, templess foundation. Go to result. Okay, so for we have minimum and maximum stresses with the dam body. Minimum means negative stresses, those are compressive. Let's see solid stresses, uh, minimum principal stress. Okay, so this is the minimum stress. I mean, minimum in some, I mean, flexural member, it may be. So I'll just switch it off so that I can have stresses in this concrete. So M20 concrete. For M25, we have to design reinforcement for the flexure. So here also the tensile stress is of the order of 0.005, the minimum. Okay, otherwise the minimum maximum, I mean the maximum compressive stress, this is of this order 0.5. So this is not at all significant. Okay, and we'll have to check it at the base. What is the stress? So let's see the tensile stresses here. Okay, so in some of the cycles it is 9.8. So let's probe where it is, this maximum tensile stress. So it is in the range, it is in this area, I mean in the at the edge and in the area of this lift well. So we have to provide reinforcement here. Other than that, let's see here, it is 4.8. Okay, still it is a bit higher than. Okay, so then it is 2.4 something. Okay, 1.89. So see, we'll consider some node, say this 4.8 node. Okay, let's see for how many cycles DCR exceeds 1. Of course, it will exceed 1 in certain cycles because 2.38 is the tensile stress, 4.83, 11985. Okay, so I'll consider 11985. Extract. So in this reach, I mean, the galleries are also near. Maybe we can have a higher grade of concrete M25 here. Okay, and probably reinforcement would also be required here. Some reinforcement in some area. Okay, what was that? Forgot here. Probe. It was somewhere here now. Yes, that was okay. 11985. I'll consider. Okay, extract. Load case E. What stresses? Solid stresses. Principal stresses for all the cycles except maximum, absolute, minimum, 11985 table. Okay, it will take some time for table to for the software to process that table. So once I get the table, I'll resume the recording. So now table has popped up. So I'll copy this data, copy and paste it somewhere first. Delete this. Okay, paste it here. Okay, so you have see in most of the cycles it is, in some cycles it is negative and some are positive. So negative are compressive stresses, positive are tensile. So let's sort it out first. Data, sort, principal stress, smallest to largest. So see all the compressive nodes we don't want, and let's see the maximum compressive stress also. So it is 0.05. I mean maximum will be somewhere down. This is, oh yeah, this is, so this is not very high. Okay, so actually we are concerned about the tensile stresses. So it is, so these are the tensile stresses. Control X, paste it here. Okay, then sort it. Sort it from this time step column C, smallest to largest. Okay, and then let's come here. Okay, so this is the allowable tensile stress. So see in USSC engineering manual, so it is in FPS system, you know this. So 20 MPa FCK 20 we have considered. So I converted into PSI, pounds per square inch. Then this is the allowable tensile strength as per Raffles formula. Okay, then this is the conversion of this PSI into MPa. So this much, this is the strength. Okay, where's that? Copy, and I'll paste it here. Okay, so this is with the DCR criteria. So let's see. I mean, see, this is so in few cycles it is exceeding DCR level of 1, but this is not the only criteria. So we have to check the cumulative inelastic duration also. Actually, it's not linear in dB. Actually, it should be. That means, see, this is dB case, no? So it should be within 1 actually. If it is MC, then probably it can exceed. So, anyways, we'll plot here also. That means this curve, I mean this portion, this is highly stressed region. This one, I mean the opening is very close here. So probably in this area, either we require reinforcement, that would be better to provide reinforcement. Otherwise, we have to increase some mass here. Okay, so from the dynamic perspective, so you can see two. So if say if I provide M25 concrete instead of 20, what is the criteria? Let's see. So even then, I mean, then 2.7. Okay. So if I provide that on this face, M25 crore concrete 2.7. So this color, okay. So above this, I mean, most of the region, in this region, either you need reinforcement or additional concrete. So below this is less than this, I mean, allowable tensile stress. Okay, Anyways, so we are running the time. Suppose, let us assume, so this is dB, this is for dB, this criteria is not fulfilled. DCR criteria, that means tensile stress exceeds the allowable limits. So for dB condition, it should not exceed that. For MC, it may exceed, then we have to find out the cumulative inelastic duration. But let's say this is MC, okay? So we have plotted the DCR, we have this, we have plotted this. So let's plot the cumulative inelastic duration. So what to do that? For that, okay, what I'll do, I don't need this. Okay, let's say DCR I need, say DCR, copy, maybe I can paste special, copy, paste special, values and number format. Okay, so now sort it, sort column T from largest to smallest. Okay, let's see. So 1.57 is the DCR, so in this range. So whether it lies within this range or not, we have to check that. Okay, so then see what I'll do. Yeah, I have to check, say 1.57 per say every 0.25 or say, okay, so up to say up till 1.2 I'll consider 1 2, let's see up, how many cycles, how many times it exceeds 1.2 level. So up to here it is 2.4. Okay, instead of this, no, scientific, I'll format this cell to number. Okay, this is better. So 1.7 up to here. So see, I'll mention here 1.57. Okay, and the cumulative inelastic duration is, I mean, cycles are 24, and each time step is 0.01 time cycles. Okay, next, I mean 1.57, it is 0, and from what is that, 1.22. Okay, and the cycles are 24 into 0.01. Okay, so this, let's now plot it for say up to say 1.15. Okay, okay, so again 1 2, so 1.15, so it is 10 divisions, so 10 multiplied by 0.01. Okay, so this is up to 0.15, and now up to say 1, let's see, 1 2, up to here, say 15 steps, 16 steps, it exceeds 1, so it should be 16. Okay, so I mean 1, it is not exceeding in this 1 point, how much, 1.22, keep 1.2 here, let's say. Okay, so I mean this, if it is MC condition, probably this would be fine. I don't know why it is happening 0.24. Okay, whatever. See, okay, so 1.57 is the highest, and if I say 1.6 for nothing, I mean there is no cumulative duration is 0 here. So why it is minus 0? I don't know. Anyways, so this is within this 0.3 to 2 range if it is MC. So, but this is not safe in DB itself. We have to do something here. So probably let's see one more, say here. Here, I mean, it's less than DC. We know that so there is no inelastic uh, uh, durations here for this node. Okay. So similarly for MC, we have to evaluate for similar criteria. That means we have to evaluate the reinforcement here, either reinforcement or we have to change its section here. Okay, we have to increase this section such that these values are less than, if I say provide M25 concrete. Okay, so these values should be less than this 2.77. Okay, so I think you have a fair idea about how to perform a dynamic analysis and pseudostatic analysis. In static analysis, this is fine. For stress analysis, for normal operating conditions, static analysis, again, this is okay. But for dynamic analysis, this region, okay, this is not okay. And here we have, I mean, we have to provide reinforcement otherwise also because of these flexural nature. Okay, and it you can view it from here also. I mean, there is a gallery here. Okay, uh, gallery here. I mean, this is also quite thin. So either you increase the, make the slope flatter here. Okay, this area is okay. No need to change the slope here. Probably, okay. Maybe this area we can have a more concrete on this side as well as on this side. Okay, then it will be safe in dynamic this ground motion time history. But still I doubt that whether the time history, provided time history is history corresponds to the seismic coefficient of 0.12, because normally it doesn't happen. If the dam is fine for static conditions, most of the time it is okay, and for sliding check and the stress check. So this is it for the NOF block. Hope uh, you would have learned something from these sessions. I'm a very ordinary engineer, but uh, having experience of about 20-25 years, whatever I have learned, I tried to demonstrate that. Okay, so I don't know how much successful I am. I mean, many of you might be knowing more than this. So if you find it not of that much use, I can only apologize to waste your time. But if you have learned something, I mean, I'll thank God that uh, I could deliver something to to you, to other fellow engineers, what I have learned. So okay, so this is it for this series. Maybe I'll come up with more videos. So next time I'm planning to record a video on radial gate analysis, and afterwards analysis of overflow block. Radial gate I'll take up first because I need to uh, apply radial gate loads in that OA block section at the trunnion beam location. So better to analyze the OA block first, and then later on I'll be analyzing, I'll be checking the OA block for stability, and then I'll evaluate the reinforcement in piers, breast wall, and trunnion beam. Okay, so for this session, this is it from my side. If you are interested, I'll upload those videos also for OA block, and later for say two-dimensional analysis of earthen dam, deepest earthen dam section, then powerhouse section. I mean the powerhouse, TG foundation, uh, and other stuff. So thank you very much. Thank you.
Thank you, Chetan sir, for these very informative videos. We have Chetan sir with us for the Q&A part. If you have any questions, please ask in the question chat box. I'm making you presenter, sir. Yeah, you are presenter now, sir. You are on mute, sir. You can unmute your mic. Yeah. Now,
Okay.
yes.
Yes.
Now,
Thank you, Vatan. Yeah, it was.
okay.
Yes. Yes, please. You please
Uh,
read the questions. I'll try to answer it.
yes,
Yes.
sure, sir, sure, sir, sure. So there is question from one of our user. When we need to analyze two or more dam block in a single model, what should be the interface between the dam blocks?
Okay. See, if you are analyzing for stresses, say OF block stresses, and you have to evaluate the reinforcement, and you can definitely consider the restraint from the side blocks. Okay. Otherwise, you may end up with a very heavy reinforcement in piers. Okay, for that interface should depend on the property of concrete, what grade of concrete you are considering it. So interface strength will depend on that, but there shouldn't be any rigid connection between those two dam blocks and NOF blocks. Okay, so only the forces should transfer, no movement should transfer between that, so interface element should be there. And so that way you can consider the restraint of the side blocks. Maybe one block on either side would be sufficient, and that way you can optimize the reinforcement.
Okay, sir. Thank you, sir. Next question from one of our user is, as per the analysis, the tension is appears on the upstream phase. Isn't
Right.
it? It would be at downstream side.
No, it is on the upstream side. I have I mean, I have to increase the concrete on the upstream side, as well as I can, I mean, increase the uh, this concrete on the downstream side also. That portion is quite thin actually, either on upstream side or down.
Mm, Your voice is not audible, Chetan, sir.
7 8 whatever MPa. So either have to increase the concrete or provide the reinforcement. So better is to increase the concrete on the
Mm,
upstream or downstream side. Yeah.
Okay, sir. For where I can I download the software? Someone asked. I will definitely get back to him. The third one is like for designing a pier, do we need to apply dynamic load along the dam axis?
Along the dam axis, yes, for designing a pier, yes, I mean, pier critical forces will be in across flow direction, across flow of the flow of the river. So you have to apply the dynamic forces, I mean earthquake forces. Either you apply a pseudostatic force. Okay, so by seismic coefficient method you analyze, or you can also simulate this ground motion time history also in a cross flow. Okay, and then check the stresses. But in that case, the tensile strength, allowable tensile strength, should be as per the Raffles formula. If you consider 0.01 FCK or 0.02 FCK as per the loading condition, you will end up with very huge, I mean, reinforcement. In dynamic condition, if you are analyzing for the ground motion time history, use Raffles formula. Otherwise, if you are considering pseudostatic earthquake force by seismic coefficient method, consider those I mean 0.01 or whatever. For evaluating reinforcement, consider 1% of FCK for only for the pseudostatic analysis. For dynamic analysis, you have to increase that 1% also. Okay, so it
Hmm.
won't be 1%. See, you are getting the stresses of the order of 4 5 MP on the upstream side.
Hmm.
If you consider that 0.01 or whatever, your dam is, you increase whatever concrete you want to on the upstream side, you will never get that. Okay, so for dynamic analysis, consider high tensile stresses. Raphael's formula you use.
Hmm.
Yeah.
So the next question is, what is the method for the reinforcement calculation? Also, when we see a section showing a stress contour,
Yeah.
when we hide few elements, the stress concentration one should be considered for the reinforcement evaluation.
Okay. See, first thing is, for reinforcement evaluation, you can find out various literature. We have the reinforcement evaluation theories for bending members, flexural members, based on the bending moment. Okay, whether it is ultimate strength or limit state method or working stress method, those are for bending members. You should have bending moment for that. Okay, for that we consider the tensile strength of concrete as zero. Entire tension should be taken by the reinforcement only, and then we actually restrict the neutral axis up to certain limit, so that the section is not uh, over reinforced. So this is these are the prevalent, I mean, theories for evaluating the reinforcement. For if we are modeling solid elements, for solid elements, I mean, we can't get bending moments from that. Or for that matter, if we are having a mass concrete, those are not flexural in nature. Okay, not bending. For that also, those bending theories are not applicable, but tension would be there. For that, we have to consider a block. Okay, from the maximum tension up to, you can consider up to 1% of FCK tensile strength. That block you can consider, that stress block. From that stress block, you can evaluate the force or tensile force. I mean, stress multiplied by the area will give you the tensile force, and that force divided by the allowable tensile strength of the reinforcement, that will give you the required area of reinforcement. 1%, it is based on experiment in some codes, in Indian code also. In one of the code for anchorages, they have mentioned that for anchorages you can go up to the 1% of the FCK, that much of tensile stress. So I mean, that 1% will approximately, if you have some flexural member, if you compute it from bending moment, that 1% will give you approximately similar reinforcement what you compute from bending moments, from bending theories. Okay, that's why we consider 1%. Okay, so that is also slightly higher than if you compute it from bending moment, but that is reasonable reinforcement you will get.
So one of the user is asking, so as a structure engineer analyzing a dam, to what extent should we know finite element analysis and dynamic analysis? Since the subject is very vast, it can be overwhelming to see all the topics. How should we approach it?
See, you should always stick to the basic wherever whatever you do. You always stick to the basic. What you are actually doing in finite element analysis also. See, force, you should know the basic definition of force. Anything which will deform a body, which will induce some deformation, that is force. Okay, when or otherwise, when some deformation is there, that means some force should be there. Okay, so in dynamic analysis or whatever analysis, these the equation of motion has to be solved. Equation of motion, if only say static loads are there, only mass into acceleration, that equation has to solve. If finite element analysis, the vibration is also there, then damping into velocity, that part is also added. And if the material property, that stiffness into the deformation, that part is also added to compute the force. Okay, these three components are only required: mass into acceleration plus damping into velocity plus stiffness into deformation. That will give you the force. From force you can evaluate the stresses, from stresses you can evaluate the reinforcement. So this is the basic. Always stick to the basic, then go through the codes. You can have Rayleigh damping, you can have modal, okay, I mean, eigenvalues, where to apply, why it is being applied here. Is it really necessary? Those things are, I mean, secondary. If you stick to the basics, you will get clarity on, I mean, on the advanced things also. Okay, so just stick to the basic. Okay, just remember, stress is equal to force upon area. Okay, stress is proportional to strain. Stress is equal to modulus of elasticity into strain. Okay, you normally for normal condition, you are going to analyze your structure within the linear elastic limits where the stress is proportional to strain. For earthquake, you can exceed that linear elastic limit to inelastic limits. Okay, and different criterias are there, though permissible stresses are there. Okay, so just stick to the basic, you will get to understand. Okay, then you can study. I mean, there is no limit to study uh, the various topics. Then there is no limit.
Yes, sir. Yes, sir. No limit to study is the key.
Yeah.
And so, yeah, so I think there is no question left. So, lastly, on the behalf of entire Midas team, I would like to extend our heartfelt gratitude to you, sir, for presenting this comprehensive webinar series that is finite element modeling and analysis of hydropower structures. Your in-depth coverage of topics, including modeling of dam, NOF block static, as well as the dynamic analysis, has been incredibly insightful, and it is like beneficial for all the attendees as well. Your expertise and dedication have provided immense value to the audience, I guess, like because for me it is very informative, and it is also like equipping with the practical knowledge. So me and my our audience, they can apply the same in their work. And thank you for your time, effort, and commitment to making this series as a successful series, sir. Thank you, sir. Thank you. So, like I really like these sessions. These are very informative.
Yeah. Thank you. Thanks a lot. I really thank Midas for giving me this platform to present these webinars. Thank you everyone whoever have attended. I mean, you can contact me also, otherwise also through LinkedIn or maybe Vatan or anyone from Midas can provide you my contact mail IDs and everything. So I'm available to answer your queries anytime. Okay. So I'll be
Okay.
happy to
Okay.
discuss any technical issues. Yeah, thank you.
Thank you, sir.
Thanks a lot.
Thank you,
Yeah,
sir. Thank you. Bye bye, all of you. Thank you, sir. Bye bye, sir.
bye, bye, bye.